Okay, using better words than I used at the end of the last one, we're going to talk about each term of this. Now, first of all, we're going to say that we've got a resistance here, and then we have two things here. Now, since the sines and cosines are unitless, the units of this and this had better darn well be units of resistance. Well, you can easily, in terms of the definitions of the farad and the Henry, verify that reciprocal omega c has units of resistance, as does omega L. But why would they appear in this function with units of resistance? Why does the inductor give us something like resistance, and why does the capacitor give us something akin to resistance? Okay, well, let's talk just a little bit more about some terminology, and within the conversation we'll talk about how capacitors actually work with high frequency and low frequency, just in terms of our experience. Okay, capacitive reactance, well, this 1 over omega c, which we call X sub c, that's our capacitive reactance. It has the units of resistance. And we're going to call this inductive reactance. That's on another board. We'll get to that very quickly. Okay. So this says that this capacitive reactance, when omega is very small, omega being in the denominator makes the capacitive reactance very big. And when omega is very big, that's going to make this capacitive reactance small. Now, why would that be? Well, let's consider. You've got a capacitor and you're charging it. Now, we've done this with a crank. You know, if we crank forward, backward, forward, backward, forward, backward very rapidly on our 1 farad capacitor, the mechanical resistance in the crank doesn't differ much from what it would be if we're just cranking straight for a short time. Now, we know that as we continue cranking, if we keep cranking in the same direction, the cranking is going to get easier. And why is that? Well, that's because a high mechanical resistance here, if we've got to exert a lot of force here, that's to move a lot of current through the circuit. So more force means more current, okay? Less force, and that's what we get. We get less and less current as we keep cranking. Now, if we just crank back, forth, back, forth, back, forth, we keep cranking pretty much the maximum current. And why is that? Well, that's because if just a short crank forward, short crank backward doesn't charge the capacitor up very much. We don't have time, we're not taking the time to transfer very much charge. And of course, whatever we transfer when we crank forward, we're going to transfer it back when we crank backward. So the backward-forward cranking never charges the capacitor up very much, so the capacitor really does very little. Okay, well, that's an example of a high frequency versus a low frequency. If we keep cranking, if we crank it for 5 minutes, most of that 5 minutes we're going to have very easy cranking. After about 20 or 30 seconds, the cranking gets very easy, and all we're really doing is we're cranking against the friction in the apparatus. So we can feel, and of course we can put meters and oscilloscopes in these things, we've done this, and we can see that the charge on the capacitor, the current in the circuit with just a capacitor and a generator very quickly, well, with some time constant, approaches zero. If we crank this thing for 5 minutes, we go through many time constants. So we, for the first 20 or 30 seconds, maybe we're doing a little work, and after that, there's nothing going on. Okay? Which means that if we average our current over 5-minute cycles, our average current is very low. Okay? So, fast cranking, we don't do much to the current. The capacitor acts like something that has very little resistance to our creation of the current. If we crank over a long cycle, well, the voltage goes like this, the white lines, okay, and the current does this, okay. It decreases, actually it decreases to a double amplitude here, But if we've been cranking for a while, it just kind of does this. It decreases and then stays near zero for a long time, decreases and is near zero for a long time, decreases near zero for a long time, if you're changing the current slowly. Okay, so if omega is small, that means you're cranking in one direction for a long time, you're cranking in the other direction for a long time. Now, this diagram shows a square wave. A sine wave would act a little bit differently, but you still get the idea that if your wave takes a long time, for most of that time you don't have much current. Okay, so that kind of tells you that if omega is small, meaning you're taking a long time for every cycle, that gives the current time to approach zero, essentially. So you don't have much current. If you're cranking very quickly, the capacitor doesn't have time to charge up. It doesn't have any real effect on your circuit. So that's as much of an idea as we want to carry away right now. And the way I say it, big omega, it acts like low resistance because very little charge builds ever. And the capacitor does almost nothing. For small omega, capacitor does quite a bit. It charges up and then prevents, it charges up, gives you a back voltage that's equal to your source voltage, and you get very little current. Small omega, current spends most of its time near zero, so 1 over omega c is high and acts like a high resistance, because a high resistance gives you essentially a very low current. Okay. Well, that's the way the capacitor acts. Now I've got it on a different board, so we'll do a different video. We'll see what inductive reactance does.